Today I'll be doing some performance testing so we can learn as much as possible about the performance of coroutines in Unity. On this particular test environment, I've set up a very basic scene. There's a camera, directional light, and a single cube that is showing in the background. On the cube is attached this script called performance testing, which I will get into in a second. But before that, this is running Unity version 5.3.1 F1. So even at the time of this recording, it is a little bit out of date. I will be running this with a more current version of Unity at a later point in this video, but I want to start here to maintain a roughly chronological order. This is the performance testing script, which will be kept as basic as possible. First, there is the number of items, which defines the number of coroutines that will be run every frame, and an array of booleans, which is not serialized so that the Unity editor doesn't get in the way. And the start function will start one coroutine per item in number of items and run that coroutine every frame. The coroutine picks a number based on the index that was passed in, increments that number every frame, and sets its personal index into that Boolean array to be either true or false based on whether that number is even or odd. It then waits for the next frame and goes on and does that again. In other words, if I set the number of items to 1,000, then 1,000 coroutines will be started, which will run every frame and set a Boolean to true and then false and then true and then false every frame. So it's one of the simplest possible coroutines, which makes it quite appropriate for performance testing. So this initial test is going to run 0 coroutines, just so that you can see how the profiler looks in a relatively empty scene with pretty much nothing running. So what we have here is quite a few frames per second. Let us call it 1,000. And if we dig into it a little bit, we find overhead is running kind of often, but it's not really slowing things down. This spike is graphics waiting for the frame rate. And all of that is happening because it's running at 1,000 frames a second, which is excessive by any measure. So if we set this number of items to something greater, like 10,000, then we will get a lot more work being performed. Anything that is different between what you see in the no work scene versus what you see in the work scene has to be the result of changing the number of coroutines that were run. So I run this for just a little bit and we see a lot of work being done. Now if we dig into this a little, we find that the profiler is telling us that coroutine.moveNext is only using about 3.8% of the processing for this frame. Of course, there's that other little process down at the bottom that's another 0.8%, so roughly 4.5% of the processing is being used on this frame, according to the profiler. And we might believe it if we had a very complicated process and we didn't have that chart right to the left of it that tells us that there's more to the story. What you will also see if you dig into these processes is that each and every coroutine created by Unity in this version allocates 17 bytes per coroutine per frame. If you are somehow stuck on a version before 5.4, then you either have to live with it or you have to find some alternative to Unity's coroutines. And the situation isn't so great in 5.4 either, but I'll go into more detail on that in a moment. Right now what I want to talk about is the difference between the graphs running no coroutines and the graphs running 10,000 coroutines. As you can plainly see, most of the cost of these coroutines is not being attributed directly to the coroutine. It's actually being put under the header of overhead. In almost any other context, the overhead would be the processing that is endemic of the environment that you are on. So if you have a task that Mono has to perform in order to keep its environment up, perhaps to arrange its buffers in a particular order because of some internal process, then that's what you would normally consider to be an overhead task. It would not really be attributable to any particular process or anything that is really relevant to you or me. But in this case, overhead seems to be something that is attributable to a specific process. In this case, overhead is being caused by me creating 10,000 coroutines and running them every frame. It would not be there if I was not running those 10,000 coroutines every frame. Overhead in this case is a direct cost of running the coroutines. It should be attributed to the coroutines, but the profiler, for some reason, is not attributing it to those coroutines. Overhead isn't only incurred when you run coroutines, it is actually also incurred when you run an update loop or on-draw gizmos or any of the other named functions that you can hook into in Unity. What overhead probably represents is the computational cost that is incurred when switching between managed and unmanaged code. In other words, between C++ and C#. So in that sense, it's quite a real thing. I think that it is badly named in this case, though. So for the remainder of this video, I'm going to call overhead context switching cost. So real quickly, let us see what happens when we take those same 10,000 coroutines and run them using mech. The mech definition is almost exactly the same as the Unity definition. As you can see, it's using the same lines except for two slight differences. The I enumerator is of type float, and we are returning 0f, which both of those are just the differences in how mech handles coroutines versus how Unity handles coroutines. So when we run this, we can see two things immediately. One is that it runs about twice as fast as Unity's coroutines, and two is that there is no context switching cost. If we drill in a little bit to behavior update, timing.update.processing coroutine, we find that it also has no GC Alex per frame. Okay, let's move on. At the time of this video, Unity 5.4 is in beta, and at one point there appeared this tiny little note in the release notes. It doesn't appear in the later release notes, and you have to scroll all the way to the bottom of the page in order to see it. But right near the bottom, there is this little note. Fix to avoid allocating GC memory during coroutine iteration. Well, that certainly sounds promising. Let's see if that means that those garbage collection spikes are gone in the new version. So here I have the exact same scene loaded in 5.4.0 beta 20, which is the latest version at the time of the making of this video. So this is the exact same scene and the exact same code. The only thing I've changed is the version of Unity. So let me run this. I'm going to run 10,000 mech coroutines first, and we will see how that looks, just because I usually run the Unity ones first. Okay, well that graph looks normal if you ignore the fact that you're usually looking at it when the scale has been expanded by some kind of initial allocation spike. But we'll expand the scale as soon as I run Unity coroutines. So now if I run Unity coroutines, we can see how they compare to mech coroutines. Well, it looks like the profile for coroutines, which previously hadn't changed since Unity 2, has changed in version 5.4. And it appears like it has gotten better. For one, the context switching task has been reduced from about 90% of the graph to something close to 50% of the graph. So that makes things a little more honest in the profiler, at least. And, more importantly, the memory spikes seem to have disappeared. In fact, all of the per frame GC Alex seem to have gone away. And I've done some side-by-side comparisons between the coroutines in Unity 5.3 and Unity 5.4. And I have found that in terms of processing, the coroutines in 5.4 are approximately 8% faster, which is not a huge improvement, but it is an improvement. In the past, I have said that mech coroutines are about twice as fast as Unity coroutines. Now, this was being generous to Unity coroutines because mech coroutines were really more like 2.2 times as fast. But now, since Unity coroutines have gotten slightly more efficient and Mech coroutines have remained exactly as efficient as they were before, it is now more like twice as fast. Alright, before we declare that Christmas has come early and this whole memory allocation problem has been solved for Unity's coroutines, let's dig a little deeper. Now I usually just yield return null for the same reason that I put an F after all my numbers if they're float values, just because it's theoretically better, even though in reality it usually just gets optimized by the .NET compiler to the most efficient version of itself anyway. But let's see what happens if I do something that I end up seeing a lot in the wild, returning 0 instead of returning null. Oh no, it looks like the garbage collection spikes have returned, after we'd just gotten comfortable with not seeing them. Well, let's take a closer look. Apparently, each coroutine is allocating 20 bytes per frame. Well, that is not so great. Does that only happen when you send a variable that's unrecognized? Or does it happen with one of the several named classes that Unity uses? Like wait for seconds or wait for end of frame? Let us find out. I'm going to copy the example that Unity has posted on their documentation for wait for seconds and see how well the official example performs in the new version. So I'm going to have to run this for 5 whole seconds before any of the coroutines will actually execute. But before long, we should see a spike. There it is. Well, it looks like the command yield return new wait for seconds 5 creates 20 bytes per coroutine per frame that coroutine actually executes. So that's not looking so great. Let's compare this to Mech coroutines. Of course, the way you define it is just ever so slightly different. You use timing.waitForSeconds instead of new wait for seconds. And then you run your coroutine and wait a full 5 seconds. There's the spike. Okay, let's see what it looks like. No GC Alex. Alright, well let's switch back to Unity coroutines because I think there might be a way to structure your coroutines so it doesn't actually have that per frame allocations. It looks like the culprit is probably creating that new wait for seconds variable in order to return it in the yield return. So instead of creating a new version of that variable every frame, let's just initialize it once at the top of the coroutine. That will create 1 GCalloc per coroutine instead of 1 GCalloc per frame. And I'm going to change the time frame from 5 seconds to 0.5 seconds because I'm tired of waiting that long. Alright, it looks like if you structure your coroutines that way, you can avoid the per frame allocation. That is nice to know. I'm going to skip things into fast forward real quick here. Perform a comparison with Mech again, just for clarity. And I'm going to do the same kind of thing with wait for end of frame. First I'll yield return new wait for end of frame. And then I will do an experiment in which I perform the same kind of thing, pre-caching the variable and returning that. Alright, it looks like wait for end of frame behaves the same way as wait for seconds. Now let's take a step back and look at what we've discovered. One of my degrees is in psychology, and we had this saying that the word but is actually an acronym, which means behold the ultimate truth. Now I know it's not literally true, but pay attention to the but in this sentence. We've found that you can remove all per frame allocations from Unity coroutines after version 5.4, but you have to arrange your coroutines in a very specific way in order to do that. Or you can use mech for your coroutines, which not only runs faster, but I've also architected it in such a way that it will not allow you to be inefficient with your memory, at least not in your yield return statements. I think it is a lot easier to say, here you can use mech to do what you need to do, than it is to say, never yield return new wait for end of frame, never yield return 0, always use null, and always pre-cache the classes that you pass in to yield return, or else you will get a GC alloc from that. All those rules. I don't know about you, but I'm sticking with mech.